welcome to this last lecture of this course, semiconductor optoelectronics, and I call this last lecture as epilogue. So, let me first recall what we had studied in this course, and then we will discuss a topic that is integrating various devices, semiconductor optoelectronic devices into a photonic integrated circuit. So, we started with in part 1. So, in part 1, let me just recapitulate. We discussed about the basics or basic physics of semiconductor optoelectronic devices, that is basics of semiconductors, for optoelectronics, Semiconductor physics, as we mentioned, is a very broad topic, and we have covered only the essential part of it for optoelectronics, semiconductor optoelectronics. In particular, we have discussed here density of states, because as we have seen through the course, density of states plays an important role in the device characteristics and device performance. We then discussed about semiconductor optoelectronic materials. So, materials for optoelectronics, semiconductor materials for optoelectronic, and also we discussed about the heterostructures and need for heterostructures. In the second part, in part 2 of the course, we discussed about emission, absorption, modulation and amplification. In particular, we have discussed two devices here, the electro absorption modulator EAM, electro absorption modulator, and the semiconductor optical amplifier SOA. So, two devices we have discussed in this part, electro absorption modulator and semiconductor optical amplifiers. Then we came to part 3, which was semiconductor optical sources, semiconductor optical sources, Here we have discussed about light emitting diodes, LEDs, and a variety of laser diodes. And finally, in part 4, semiconductor photodetectors. So, here we have discussed about, of course, the PIN and APD, in particular PIN and APD, PIN diode, and other detectors. So, if I may list the modulator, the amplifier, the source, and photodetectors. So, we have the modulator, the source, modulator, amplifier, the amplifier and of course, the photodetector. These are actually the basic ingredients of a communication system. So, a communication system, as we started in the first class, has a transmitter here, a transmitter, a link which is of course a passive link. There could be amplifiers here, amplifiers, and then finally the detector or the receiver. The receiver, transmitter, link, amplifiers, in between there may be amplifiers and receiver. So, the transmitter, apart from the electronic circuitry, comprises of a source, an optical source in optical communication, an optical source and a modulator, and there could be a power amplifier which boosts the power at the transmitter itself, and there could be inline amplifiers, and similarly at the receiver we may have a pre-amplifier. The receiver would have a pre-amplifier, an amplifier here, and then of course, the processing circuit which may comprise of filters and photodetectors, demultiplexers and so on. So, these are the important basic building blocks of a communication system. Just as in the case of electronics, where several components could be combined or could be integrated on a single chip, the question is it possible to integrate these devices? We have studied the devices independently as standalone devices, but is it possible to integrate these? And that brings us to what are called PICs or photonic integrated circuits, photonic integrated circuits. Integrated circuits or simply called PICs, PICs, photonic integrated circuits. As the name indicates, it refers to integration, this refers to circuits or devices where two or more optical functional devices, it refers to integration of two or more optical functional devices on a single chip or a substrate, on a single chip. PICs are picking up now, they are becoming important. So, let me briefly discuss some aspects of these photonic integrated circuits, and as I have written, it refers to devices which have two or more, several functional devices on a single chip. A simple example would be, so let me pick up a simple example of a tunable DBR laser, because the functional elements, the functional devices could be passive devices or active devices. There could be passive devices or active devices. So, let me pick up this tunable DBR. We have already discussed DBR laser, distributed Bragg reflector laser. Recall that the DBR the DBR laser has a double heterostructure, the lasing active region here, and this may have one or two frequency selective elements. What we had discussed earlier was with the two frequency selective gratings at the two ends. So, this is what we had discussed, and this is a longitudinal cross section of the device. The device is like this, we are looking at the longitudinal cross section, the simplest longitudinal cross section, and here is the metal electrode and the electrode here. There may be many more layers here, I am just showing the essential layers. So, the gain region, so here is the optical mode which propagates along the double heterostructure here, and these are the electrodes, say plus and minus, a current I is flowing through this. The two ends are AR coated, anti reflection coated, AR coated. AR coated to avoid any reflection from these ends, because we need these frequency selective gratings. So, these are the frequency selective gratings. Frequency, this is the DBR, not the tunable DBR. I am discussing the DBR that we had already discussed, frequency selective element. The period is the periodic structure. So, the period here lambda, the period is such that if we choose lambda is equal to lambda 0 divided by 2 n effective, where n effective is the effective index of the optical mode. Here is the optical mode which is propagating back and forth. If the period is such that it is equal to lambda 0 by 2 n effective, then lambda 0, the wavelength here, this is the optical wavelength, this is the grating period, lambda 0 would resonantly get reflected at this periodic structure, the periodic grating, leading to feedback at this wavelength only. So, feedback comes at this wavelength, which means feedback that is so essential for laser oscillation comes only at this wavelength, thereby leading to realization of a single frequency laser or a laser oscillating at one frequency. One frequency we refer to one longitudinal mode. Of course, there is a finite frequency spectrum associated with it. So, this is the DBR that we had studied. There is a passive frequency selective element here, and this is the gain medium, and laser oscillation takes place because of these frequency selective. The single frequency oscillation is ensured by the periodic structure. In a tunable DBR structure, there is no need of having both the frequency selective elements, we can have only one of the frequency selective elements. In a tunable 2 segment tunable DBR, we have this region, that is the active region right up to the end, and then the cladding region. In the cladding region, we have the periodic grating over one end of this, and we have this end anti reflection coated, AR coated. This has two separate electrodes now. So, the laser is treated as a 2 segment device here. There are 2 electrodes. So, there is current I 1 and current I 2. So, the current I here, again longitudinal cross section of the device, This is what we had already discussed. And here we have a device where we have two currents passing through the same device. There are two electrodes. The current I 1 primarily determines the gain here. This is the active region, and the mode propagates here. So, the mode propagates through this structure. Okay. The active region, the current I controls the gain of the active region and hence the power output, whereas the current I 2 here, I 2 is primarily to control the selected frequency, because a current injection leads to a variation in the refractive index, and as we have already seen, in this case the current was not flowing through the periodic grating element here in the ends, current was flowing only through the active region, that is gain is provided only here in this. So, there are no current flowing here, and therefore, the frequency selection is done by these gratings. Even if you vary the current here, the frequencies do not change, because frequency selection takes place in this region by these gratings. However, in this case, because current also flows through this here, the frequency, the choice of frequency which oscillates will depend on the N effective, which depends on the refractive index of the mode, refractive index of the region here. Therefore, N effective can be affected. So, we have lambda oscillation is equal to twice N effective into lambda here. The lambda oscillation can be varied by varying the N effective. Lambda, the grating period is fixed, By changing this N effective, it is possible to vary the frequency of oscillation. So, we have two different currents here, one current determining the power and the gain in the medium. The second current determines the injection of carriers into this, so that the variation of effective refractive index in this region is determined by the second current, and therefore, N effective is controlled by the second current, and therefore, the output frequency is controlled by the second current I 2. Please see that this has two segments, two functional elements. One is the gain region and the second region is a frequency selective element. Is a active, both are active regions. The frequency selective element is here, and so this is, for example, a simplest PIC, a two segment, a two element PIC, photonic integrated circuit. We can have many more complicated and complex PICs. For example, if we take a WDM transmitter or a receiver, the current day WDM systems, using a PIC, if we were to realize a WDM transmitter or a WDM receiver using a PIC, the general layout would be like this. Let me show the layout. So, we have lasers, let us say a 10 channel WDM system or a 40 channel WDM system, could be 10 Gbps. More recently, there has been work reported where 100 Gbps, 10 channels of 100 Gbps systems were integrated on a single PIC to realize transmitters. So, these are the LD 1 standing for lambda 1. So, this is wavelength 1, LD 2, LD 3 and so on. So, these are DFB lasers. So, DFB lasers, single frequency stable DFB lasers, LDN. If there are n wavelengths. So, lambda 1, lambda 2, etc., lambda n channels. The output of laser diodes here passes through a modulator, which is an electro absorption modulator EAM. The second device modulator EAM. So, this is LD laser diode. Here we have EAM electro absorption modulator. This is an SOA amplifier, and this is a photo detector, maybe pin or a. So, EAM electro absorption modulator, EAM 1, 2 and so on. So, let me write it EAM. The output of these, there could be more elements, there could be amplifier right here, or the output of this goes to a mux, an AWG mux. So, this is AWG mux, AWG stands for arrayed waveguide grating. Let me briefly discuss about this AWG, arrayed waveguide grating. These are now almost one of the fundamental blocks, building blocks in WDM and DWDM PIC transmitters based on photonic integrated circuits. So, AWG here. So, this is lambda 1, lambda 2. The output, this is a mux multiplexer. So, we have n lambdas here. So, here is the output which has all the wavelengths coming here, lambda 2, lambda 3 and so on. There could also be an SOA here. So, there could be an SOA before it goes over to the transmission line, to the fiber link. So, this whole thing could be integrated, for example, on a single semiconductor chip, the whole thing. So, there are reports of realizing such PICs. So, PIC, this is a PIC. Typical dimension could be 10 mm by 10 mm. So, just I am giving some typical idea what is the dimension that we are talking. So, 10 mm by 10 mm or 15 mm, that is the kind of dimensions that we are talking of for a PIC. So, this is a PIC transmitter, this is a WDM transmitter, this could be a DWDM transmitter and a multiplexer. So, we have laser diode, the first device there, EAM electro absorption modulators, and of course, multiplexers. I have not discussed this multiplexer because this is not a semiconductor active device, it is a passive device. This multiplexer is a passive device. Let me briefly discuss this, and then as you see the SOA is here. The receiver could be, so let me draw the receiver as well very briefly. So, here is the receiver, the input with all the wavelengths lambda 1, lambda 2, lambda 3, lambda n enters the PIC here, the input. First, it is usually there is a pre-amplifier SOA, an SOA pre-amplifier, and then followed by the demux. So, demux, AWG demux, there could be more components, AWG demux, and then it goes to the different channels, different wavelengths going to different photodetectors. So, photodetectors. So, the input containing all the wavelengths are amplified by an appropriately chosen SOA. There may be gain flattening filters associated with this. So, that there is a flat band, flat gain band, which is followed by a demux, AWG demux, and the different wavelengths are then sent to high speed photo. These are high speed photodetectors, lambda 1, lambda 2. The output of the photodetector of course will be electrical here. This goes to further electronic circuitry. So, electrical output for further processing, electrical output for processing. So, this is a receiver PIC or PIC receiver. As we can see, almost all the components of a current modern transmitter and receiver, we have discussed the basic building blocks in this course, except the AWG MUX, which is a passive waveguide device. And currently there are hundreds of such components integrated on a single chip. So, initially there were only lasers and modulators, or modulators, and then at the output photodetectors, amplifiers and photodetectors, where amplifier and photodetector were integrated, but now hundreds of components are integrated to realize a single photonic integrated circuit. We all know the importance of integrating components, ICs, the importance of electronic ICs, we know, where of course tens of millions, hundreds of millions of components are integrated on a single chip. Comparatively, the numbers are very small. The number of components integrated on a chip is much smaller compared to the millions or nearly billion component on a single chip. Nevertheless, the advantage of integrating components, for example, the advantages of integrating components is very well known. The first one is of course compact. It makes a compact device. Most important, very low power consumption, much less sensitive to thermal fluctuations, because the entire chip is maintained at, unlike discrete components, the entire chip is maintained at a particular temperature, and many more advantages, reliability and so on. So, the same advantages are true for these as well, and PICs are picking up in a big way in the current optical communication scenario. So, let me, before I wind up, let me just briefly discuss this AWG. It is a very interesting device, very interesting optical device, which can be analyzed by classical theory of diffraction. The design comes from the classical theory of diffraction of light. So, let me consider a demultiplexer, AWG demultiplexer. So, in the remaining 10-15 minutes, let me briefly discuss the idea of a AWG MUX demux. So, here is the AWG. So, let me start with the arrayed waveguides. There is an array of waveguide. Some drawing practice here. So, an array of waveguides I am showing only a few of them. In practice, the number of waveguides. So, these are the waveguides. So, what we see is top view of a chip. So, in all the diagrams that I have drawn here, what we have seen is the top view. So, it is looking from the top. So, the chip is here and what we are seeing is the top view of a chip. An array of waveguides. Okay, let me show all of them without leaving any gap. So, I think we will have 5 waveguides. The number could be much larger, but I have chosen 5 here just to distinguish. So, these are optical waveguides. So, channels, light channels, here. So, which enters here, the channels which are opening into this free propagation region. These are FPR or free propagation region, FPR, free propagation region. So, I am showing this DMUX, free propagation region. So, this is another FPR. So, FPR. So, here is the input, that is this input, the input which is entering the DMUX is here. So, here is the waveguide, an optical waveguide made on the semiconductor chip. So, here is light entering this, all the wavelengths lambda 1, lambda 2, lambda 3. Let me take 3 wavelengths, just 3 wavelengths to illustrate 3 different wavelengths. Which are demultiplexed. So, 3 wavelengths. I will not go into the design mathematics, but concepts only. I will just be able to discuss the concepts. So, the 3 wavelengths lambda 1, lambda 2, lambda 3. So, let us say this is the, there may be several components on a single chip, but I am showing that this is an AWG chip. So, lambda 1, the input is the multiplexed wavelength stream and output is lambda 1, lambda 2, lambda 3, which could then be coupled to optical fibers if required, or it could be coupled to the photodetectors. Light which is entering here, the multiplex channels. So, this is the free propagation region. So, there is diffraction taking place. So, light diffracts into all the channels here, all they are actually quite close. So, light enters. So, there are many, therefore, almost all the light is collected, but I have shown only 4. So, it looks as if there is a large gap, but a major part of the light which is propagating through here is collected by these waveguides, or they excite the modes of the waveguide, which then propagate along this arc. As you can see that if this is L1 length, L2, L3, L4, L5, usually they are all of the same dimension. So, that the modal effective index N effective of the guide or Ng, N effective of the guide, the guides, waveguides are identical. So, if L1, L2, L3, L5 are different, are the lengths of the various waveguides here, then when they reach here, there is a propagation delay between the adjacent, there is a phase delay between the output which is coming from here output which is coming from here and so on. The phase delay or the path delay, the path difference is delta L, if delta L into N g is the path difference multiplied by of course k naught will give you del phi, the phase difference. So, this delta L here corresponds to L 2 minus L 1 or equal to, generally they are this can be taken such that they are equally separated, or L 3 minus L 2 and so on. So, the light which is reaching here has a constant phase difference, between the light which is emerging from here. Please see that these are all single frequency lasers, and therefore, the coherence lengths are very large, and therefore, even if we have a phase difference here, a path delay, they are all well within the coherence length. And so, all of them with respect to this, if I say the phase here is phi naught or 0, then this is phi, this is 2 phi, this is 3 phi and this is 4 phi and so on. So, they come at different phase differences. It is possible that these phi could be integral multiple of 2 pi, in which case all of them are in phase, or they could be in different phases. So, depending on the phase difference phi, the output could, depending on, so this is del phi is equal to k naught. So, this is equal to 2 pi by lambda. So, lambda is different for the different wavelengths, and therefore, if lambda 1 enters from here, let us say that the phase difference corresponding to lambda 2 is 0, phi is equal to 0, then the phase difference will have a certain minus phi here corresponding to lambda 1, and corresponding to lambda 3 this could be plus phi. The phase differences are different here for the 3 different wavelengths. If the phase difference is 0, then all these waves, when they propagate, because they are situated on a arc of certain chosen radius, there is a radius r here, radius r, so that all of them focus to this wavelength. So, all of them, all the light which is coming from here are in phase, and therefore, when they diffract, they focus at one particular wavelength, one particular spatial point, and there this wavelength, this waveguide is located at that spatial point, which means that particular wavelength will come through this waveguide. It is easy to understand this if we recall the basic theory of diffraction from multiple point sources. In the theory of diffraction from a single slit, we may recall, or phased array antennas. So, those of you who are familiar with the phased array antennas, so we have point sources or sources here, which are, the sources are emitting in, if I consider these as optical sources, they are point sources. If I consider these as point sources, then each one of them is emitting like this. If the input here is a plane wave, which means all the point sources, so this is the input, what I am describing is diffraction by a single slit. So, we are all familiar that in deriving the diffraction pattern of a single slit, a plane wave which is incident here. So, the slit is considered as comprising of multiple points, and then we determine the interference pattern due to these multiple source points on the screen, which is placed at a distance d. at a distance d or capital D. And then considering the path difference between them, we obtain the diffraction pattern, the standard diffraction pattern, which is the Airy pattern. So, we get maximas and minimas here. So, we get this pattern so that the peak remains exactly in the center, peak exactly. Okay, let me show the slit here. So, these are the various points. Peak remains exactly on the center, at the center, and here is the diffraction pattern that we get. This is by assuming that all the point sources are in phase, but if we assume that these point sources are separated by a phase difference of phi, then depending on the phase difference phi, the peak will shift to that side or this side, depending on the phase difference phi. A constant phase difference phi will lead to different positions of the peak, and by continuously, if we continuously change the phase difference here, it is constant, but if we change phi, the angle. So, when phi is equal to 0, let us say here is the antenna, this is the principle of phased array antenna. Phased array antenna. So, when phi is equal to 0, if here is the antenna, then the output predominantly comes in the forward direction, and if you give an appropriate curvature, then it is possible to focus the beam at a particular distance and at a particular spatial point, appropriate curvature given to the antenna. If without mechanically changing the position or the orientation of the antenna, it is possible by simply changing the phase here, relative phase between alternate sources here, it is possible that the output comes at this angle or whatever angle, and if you sweep this phase phi, then you can sweep the direction in which the EM wave is focused. This is the basic principle of phased array antenna. It is the same thing here, that if all of them are in phase, which means integral multiple of 2 pi, they will come straight here and focus at the radius of curvature of this curve here. Now, if there is a phase difference phi, 2 phi, 3 phi and so on, then they will focus at a different point, they will come and focus at a different point. So, all the light here now comes and focuses at a different point. Similarly, if instead of phi, if we have minus phi, then all of them will focus at the third point here. These waveguides, the position of these waveguides are located such that it is at the focus of these, the focus of the output from these waveguides. Now, phi or minus phi is determined by the wavelength. So, one can choose delta L, that is the structure here design. Delta L is chosen such that delta L and the positions of the output waveguides are chosen such that at wavelength lambda 1 all of them focus here. So, that lambda 1 comes out of this, because there is a constant phase difference, therefore, it does not come straight, it comes at an angle. At the center wavelength lambda 2, all of them focus at the radius of curvature of this, at the center here, center of this radius of curvature. So, all of them focus here, and at the third wavelength lambda 3, all of them focus here. So, that is determined by delta L, because Ng determined by the dimensions of the waveguide, the refractive index and the width of the waveguide, the mode effective index, and k naught contains the wavelength. Therefore, delta phi is different for different wavelengths. It is constant from one array to another. It is an array of waveguides. From one waveguide to another waveguide, adjacent waveguides, the difference is the same, phase difference is the same, but that phase difference is different for different wavelengths, and therefore, the output will focus at different spatial positions. Accordingly, the location of the output waveguides are positioned. So, what we have is a multiplexed input. I have illustrated considering only 3 different wavelengths. The number of waveguides here in the array has nothing to do with the number of wavelengths, but it depends depending on the requirement of resolution and depending on how much loss can be tolerated, there could be different number of waveguides in this array. So, the input here enters the free propagation region, diffracts. So, all the channels are carrying all the wavelengths, all the waveguides are carrying all the wavelengths. Here different wavelengths have different phase shifts, and therefore, accumulated phase is different, and therefore, they focus at different points. The output waveguides are then located at the appropriate positions. So, we have a demultiplexer functioning like this. As I said, the whole dimension could be 5 mm by 5 mm or less. So, it is a very small device, and details of the design we are not going into, but this is a very important device in realizing transmitters and receivers in DWDM systems. So, we have discussed most of the components of a photonic integrated circuit, and more peaks would appear in the new communication systems with the to exploit the advantages of integration. Both in terms of the design and fabrication, there are several challenges, in particular reducing the loss, reducing the crosstalk among the various channels in an AWG. These are being discussed, these are being looked into. So, there we come to the end of this course. Because of time limitation, we have to stick to whatever is possible to cover in this course. As I said right at the beginning in the first course, that this is an introductory level course, and I have dealt with it in a introductory self-explanatory level, and there it is. All good things have to come to an end. So, I close the course here.